Hi, good evening. This is Mustafizur Rahman. Today I am going to explain the RTree index structure. So, in overview, RTree consists of root, internal nodes, and leaf nodes. Root holds pointer reference to largest regions. Internal nodes store pointers to child nodes, storing data bounded within the parents area, and leaf nodes store actual data within the respective MBR. So here TU is the root node, NPQ and RS is the internal node, and these are the leaf node. Another important thing is MBR, minimum bounding regions, actually, which is subregions within entire space that group data as efficiently as possible. So this is the insertion process of RTree. This is the simplest form where object automatically fits into the MBR, and this is insertion when MBR needs augmenting. So here this point, actually whenever we are going to insert this point, these two MBR actually augmented. And this is partition when we inserted this object in here. This big MBR is actually participated in two group. And this is the search algorithm. In search algorithm, this is the actually query range. In search algorithm, what is actually happening, if it is not a leaf node, then it checks the every child node, and the MBR of that child node. If the MBR intersect with the range query, then actually calculate the point. So before going to the code, I want to show my analysis on RTree. So here I have taken 13 point, and b is equal to 3, and I have with this 13 point I have first created and draw the MBR, and then created the RTree, and then I have inserted another point 4 the red point, and then here I have show overflow at node U6, and then actually it is splitted, and when splitted, again node U3 has been overflowed, and it has been handled accordingly. So finally here is the MBR has been updated. So there is the search query, the search query, the green rectangle box, actually the range query. Node U1, U2, U5, U3, U8 are accessed to answer the query with the shaded search region. Now this is my actually the coding. Here I have done it in Python language. First of all, I have done the sequential query. What I have done, I have load in sequential query. I have load the data set, and read the data from the text file line by line, split the each line, and split the line with the space, and put the data in a array points, and print it. In the similar way, I read the 100 queries and put the data in another array queries. Then what I have done, I have performed the sequential query. I have reading each point from the points array variable, and uses that nested loop, reading each point from the query array variable, and actually see whether this query point is actually between the rectangle, between the query. If the point lie between the query rectangle and increase the result, then I put the result ID in a array. And then what I have done, I just calculated the total performing time to actually to execute this query, and this is my result. This is the these are the actually output of my point. These are the actually the data point, and these are the actually the 100 query point, and this is the my sequential query. I get 95 955 55 points included in this query range. And the total sequential query execution time is almost 0.89 second. Then in RTree in RTree operation, I have created two objects. One is node class and another is RTree class. In node class, this is the actually the constructor of the node, which initializes the ID, child nodes, leaf nodes, parent nodes, and the MBR, and these are the function of the node class. Perimeter, which calculate the perimeter of the node, and this is the actually function of check overflow. Actually, it is checking whether the node is overflow or not. That's just simply checking the data point length. And this is another function is check whether it is root node or not, and whether it is a leaf node or not. And this is the actually the RTree class, and here this is the constructor, and this is the main insert function, where to insert node in the RTree. So if check if the node is a leaf node. If it is a leaf node, then add the data point and update the corresponding MBR. After that, it is actually checking the overflow, and if it is overflow, then handle the overflow. And if it is not a leaf node, it has an actually finding the choose a subtree to insert the data point to minimize the perimeter and update the MBR. And this is the function of add data point. And this is the add child node function, where it is all the child nodes are appending in an array and updating the MBR. And this is the function of handle exception overflow. And during the overflow, handle the overflow. First of all, I have splitted the node into two node, and if it is a root node, then create a new root with S1, S2, and its children. And this is the function of get subtree, which actually return the child whose MBR requires the minimum increase perimeter to cover P. And this is the increase perimeter, and this is the actually split node. I am going to explain something about this. The splitting is actually happening in two ways. One is in leaf splitting, and another is another internal node splitting. In leaf splitting, now we are actually first sorting based on the X and Y dimension, and in internal node, actually the sorting is based on the MBRs. And after that, it actually returned the best two nodes, and this is the update MBR functionality. This is the search query functionality, which is actually searching, and here is this function is recursively used, actually, and this is covered whether the point is actually covered this rectangle or not, and this is the is intersect. This is some geometrical calculation of two rectangles, two rectangle intersection. Then actually, first of all, to run the this algorithm, I create a RTree object, and insert all the points in the RTree, and then calculation, do my calculation. Here the total RTree insertion time is 11 seconds, and it is created two nodes, and then I do the query operation. In query operation, in my I get 955 data points included in the query, which is actually same as the sequential query, and the total processing time is 0.01 second, which is very effective. So from my observation, I found that the RTree query is almost 52 times faster, almost 52 times faster than sequential query. Thank you very much.